Chapter number 6, Quantitative Chemistry. Now, this chapter really starts with the chemical analysis or formulae. It discusses the relative atomic masses. It tells you that the periodic table consists of relative atomic masses for all the stable isotopes for an atom, given that it is taken as a reference or in relation to carbon 12 isotopes. So you actually are talking about an average of all the isotopes of an atom, and that too a calculated average, not just a simple average. Now, we already know how to take the relative atomic mass of an element. We did that back in chapter number 2. We do understand its definition. Relative atomic mass is average mass of naturally occurring atoms of an element on a scale where carbon 12 atom has a mass of exactly 12 units. So these masses, for our own ease, instead of these difficult numbers, are then converted into very simpler, easier numbers. And we use these simpler, easier numbers, and they're a part of the periodic table. These numbers are not a part of the periodic table. These numbers are, which are actually really easy to deal with. Now, if different elements are present in different isotopes, number of isotopes, for example, fluorine has just one isotope, lithium has two, chlorine has two. If we discuss krypton, we can see five different colors, out of which four are stable isotopes. If we look at tin, tin has a number of isotopes, only one, two, three, four, five, six, seven. Seven stable isotopes can be seen over here. But there are more colors over here. It's just that we have taken stable isotopes for this one. Okay, so when we are done with this one, what we get to do is to talk about the relative formula mass. And when I use the term relative formula mass, it's pretty simple. Like if we're talking about water, as the example given over here, the formula is H2O. So we'll take the mass of hydrogen two times and we'll add it to the mass of oxygen. We'll get the mass of water. Now this one's easy. Since we're talking about a small molecule, if we're talking about a giant lattice that such as sodium chloride has, it's again going to be the same thing. So it's pretty easy. We take the mass of sodium from the periodic table, which is 23, and 35.5, the relative atomic mass of chlorine. There you have 58.5, the mass or MR of sodium chloride. So we define relative formula mass as the mass of substance, or simply speaking, the sum of relative atomic masses of elements present in a formula unit or in one formula of the compound. Now, if the substance is made up of simple molecules, mass may also be called as a relative molecular mass or MR. Formula mass is actually the term that we commonly use for ionic compounds. Now, when we discuss it like that, we can always get to the percentage composition. Percentage composition is pretty easy when it comes to that. But before I get to percentage composition, we need to understand for a couple of um, compounds for which how to take their masses. For example, let's talk about this one. This one is ammonium sulfate. How are you going to calculate its mass? With brackets written in the formula. Do you remember how we supposed to do that?
No, I forgot.
Okay, so it's like that. We take nitrogen, nitrogen is 14. We take hydrogen, hydrogen is 1. But since there are 4 atoms over here, multiply this thing by 4. Since the whole thing has twice this 2 in the brackets, so you multiply the whole thing by 2, and then you add to it sulfur, which is 32, and oxygen, which is 4 into 16, and then you're going to get the total. That's how we are supposed to do it. So 4 plus
Right.
14 is equal to 18, multiplied by 2 is equal to 36. So this is 36 plus 32 plus 64, the answer to which is right. Easy.
Yes, sir.
Good. Now you do understand what the bracket means. Now let's take one more example. Let's clear it up. The other example is going to be copper sulfate, and copper sulfate is actually a hydrated molecule with 5 water molecules attached to its formula. How are we going to do this one? Any idea?
Um, First, we're going to solve the copper sulfate.
Very good. What does this dot mean in calculation?
Multiplication.
In normal mathematics, yeah, it does mean multiplication, but here, when we're calculating the relative formula mass, it is addition. So it's copper, which might be taken as 63.5 or 64. Then we have sulfur, which is 32, and oxygen, which is 16. But since there are 4 atoms, it's 16 plus 4. Now, this whole thing applies to this, right? So this is it. This dot means this, and 1 into 2 plus 18. And that's how we are supposed to solve this part, which is solved over here. Easy enough.
Sorry, but how is the oxygen 18 at the end?
Because there is no oxygen over here.
No, but like,
Oh,
won't it be
my,
16?
yeah, it would be 16, my bad. Instead of writing oxygen, I wrote for the whole water. Yeah, you're right, it's 16.
Okay, sir.
Okay, so when you calculate this whole thing, this is going to be 64 plus 32 plus 64, and plus this is going to be 5 into 18, which is this whole thing would be 128 plus 132 is equal to 160. So it's 160 plus 90, with the answer to which is 250. Easy enough?
Yes, sir.
Good. So since now you know all kinds of relative molecular or formula masses, we can move on to percentage composition. And there are many percentage compositions given over here, but I tend to do this topic from a little bit of a different perspective, actually. So I'm going to open up a whiteboard to do this one. Give me a minute, please. Percentage composition. Percentage composition can be given in different types in different kind of formulae. So let's start with this. Percentage composition is the calculation of percentage of the composition of the substance. And when I use the term composition, I mean what is the substance made up of? The substance must be made up of a few elements, maybe metals, maybe non-metals, maybe some ions. So we'd like to calculate the percentage of the participation of each element, maybe each ion. So it can be divided into different types. For example, let's begin with the first one. This is percentage composition of elements. This is the first type. To be honest, the formula is pretty much the same for all of them. It's just that I'm dividing it into types so that you can understand how the question can come out to be. Now, in case of percentage composition of elements, percentage can be calculated by um, mass of element in compound, which is divided by the mass of compound, by which we usually mean MR. As we have studied, MR is molecular mass, and it is multiplied by 100. Pretty easy. Percentage of H in H2O would be 1 multiplied by 2 when it is taken as 1 multiplied by 2 plus 16 into 100, which is of course going to be 2 over 18 into 100, which is equal to 11.11%. So the percentage of O in H2O is going to be 16 over the whole thing again, 1 into 2 plus 16 into 100, which means it's 16 over 18 into 100. The answer would be somewhat where 88.89%. Clear now?
Yes, sir.
This includes an example with it. Now the second is percentage composition of ions, which is pretty much the same, just that we're going to talk about the percentage of ions in an ionic compound. So percentage of ions in an ionic compound over mass of ionic compound, which is really MR. It is going to be MR every time we're going to talk about the denominator. So this is going to be MR again. For example, you can talk about percentage of NH4 positive ions in NH4 twice SO4, which is equal to what? So since NH4 is like 14 plus 1 into 4, and this whole stuff is multiplied by 2, which is 2 into 14 plus 1 into 4 plus 32 plus 16 into 4 into 100. Let's bifurcate it for the third part, which is going to be, what is that going to be? 18 over 36, so 36 is divided by 132 multiplied by 100 is equal to something I don't really know. You might have to pick up the calculator and do these small parts of calculations for me.
Okay, sir, but why did we add 2 before the 14 in the mass of ions in an ionic compound?
Why do we have what?
Why did we add 2 in the
Because
numerator?
there are two ions. Because there are two ions because of this twice, right? So we have the 2 in numerator as well as we have the 2 in denominator. Remember,
Oh,
if we're going to talk
okay.
about the percentage of ions, we're going to take all the ions. If we're going to talk about the percentage of element, we're supposed to take all atoms of the element. Remember the hydrogen in the percentage composition of elements for water? There were 2 atoms of hydrogen, so we multiplied 1 by 2 in the numerator as well as in the denominator. Makes sense?
Yes, sir.
So all the atoms or all the ions are considered for that purpose. So what's the answer to this one?
27.27.
To 27.27%?
Yes.
Great. This gives you the idea about it. Now the third is percentage composition of water of crystallization. So water crystallization, sorry, it's very Can you still see my screen?
Yes, sir.
So percentage composition, mass of water in a hydrated compound over mass of hydrated compound, which is really the MR again, into 100. So let's say we're taking about percentage of H2O in CuSO4 dot 5H2O. How are we going to take it? That is 5 into 18. 18 is the mass of water really. So 5 into, actually, no, that's not how we are supposed to do it. So I'm going to erase this part. And this is 64 plus 32 plus 16 into 4 plus 5 into 18, and this whole thing by 100. So that is 90 over 250 and 200. And the answer to that is 36%.
Yes.
36? Is that right?
Yes, it's
36%. Oh, my bad. It has to be three significant figures. We can't really write 36%. It is going to be 36.0%. Okay? It has to be three significant figures. Oh, this one missed out on the previous part. Oh, it was 27.27%. Now you have all the answers. Clear enough?
yes, sir.
Now I'm going to save it as a picture and I'm going to share this picture with you. Okay?
Okay, sir.
So you have all the data in front of you. What I'm going to do is that I'm going to use a different color over here, and we are going to write a couple of questions. For example, the compound you have is FeTiCl4. Now you are supposed to calculate percentage of Cl negative ions in FeTiCl4. Go ahead. Let's just bifurcate this whole portion for our questions. You might need periodic table in order to solve these questions. So you can open up the periodic table from your book or from any of the nearby sources. So are you there? You going to solve it right away?
Yes, sir, I'm doing it.
Okay, take your time. Start recording. 4 into 35.5 into 100 for this one. You probably did this, right?
Yes, yes,
If you did this, then your answer is coming out to be 57.72. Is that what you just said?
yes.
Then that's correct. Good. Okay, let's move on. Hmm. Percentage of O in USO4 dot 5H2O. A tricky past paper question. Go ahead. If you can do this one, the second question I've just given you, you can do any of these kind of questions. You're not going to fall for any of the tricks. Go ahead, take your time. Now, the biggest mistake that students tend to make in this kind of question is that they don't really get the point of counting the oxygen atoms. There are 4 oxygen atoms in here, and this specific 5 means there are 5 oxygen atoms in here, which means we have a total of 9 oxygen atoms. So it's pretty easy. 9 multiplied by 18 over the whole thing, 250 into 100, which means 72 over 250 over 100. The answer to this one. I'm not sure whether you're right or not, but what's the answer to this one? Or do you have the same thing? Oh,
It's 28.
72. 18 into 9 is not 72, right? That's a big mistake. Wait a second, wait a second.
Yes, it's
Okay, so 18
166.
into 5 is equal to 90, and then 180. There should be around 162.
Yes.
So this is 162.
The answer is 64.8.
64.8%. Is it 162? Yes, it is 162. The whole thing is correct. You have done it on the calculator too, right? What's 18 into 9 is, or what 162 over 250 is. You have reached all of it, right?
Yes, sir.
Good, good. Now you understand what the answer and why is the answer is so clear.
Yes, sir. Could you repeat your voice? Not clear.
I'm saying now you know why the answer is 64.8%.
Yes.
Good, good. So I'm going to take a picture of it and I'll share it with you later. Now I'm going to stop sharing and I'm going to get back to the book. Okay, so we're now at back to the book, and as you can see, we have many relative atomic masses or MRs calculated over here, or how many atoms there are in the formula: carbon dioxide, calcium carbonate, ammonium sulfate, hydrated magnesium sulfate, and they have even calculated the separate masses so that it's easier for us to point out mass of any specific atom. And they also tell you how the bracket changes everything, or what does the dot means in these formula units. Here we have the formula to calculate the percentage of an element. Here we have the formula to calculate the percentage of water of crystallization. So I have already bifurcated that formula into multiple parts. Moving on, compound formation and chemical formulae. When we need to find out how the compounds form, we sometimes go with the formation of them in the lab. For example, this specific experiment is all about magnesium reacting with oxygen in the air converting into magnesium oxide. And what would be the formula of magnesium oxide then? So we properly do the experiment till we come up with the masses of what magnesium oxide is produced. Take a look at this. This is the mass of magnesium oxide produced. This is the mass of magnesium that reacted. We can always calculate from this the amount of magnesium reacting with oxygen forming magnesium oxide, or what mass of oxygen reacted with it. Some particular observations that we can make from this kind of experiment is there are a few points that we need to understand and we need to memorize them. So I have stopped at this pink portion on at the bottom of page 156. We're going to study it. Now, a particular compound always contains the same elements. That simply means that if I talk about water, water would always be made up of hydrogen and oxygen. You can't make water with some other set of elements, of course. These elements are present in the same proportion by mass. Now, there would always be two for hydrogen, and there would always be an addition of 16 by oxygen. That's how you always get the mass of water to be 18. And this is going to always remain the same. It's not just the proportion by mass, it's also the proportion by atoms. You are every time going to make water with two atoms of H, right? And you're going to make it with one atom of O. So the proportion with respect to atoms or the proportion with respect to masses remains the same always. Now, it does not matter where the compound is found or how it is made. It really does not matter whether you form the compound, same compound, water in Saudi Arabia or in Pakistan or in somewhere, some other part of the world, or how it is made, whether this was made by a simple reaction, whether it was made by electrolysis, whether it was made by some any other random process. Okay. And the proportions cannot be changed. Of course, these proportions cannot be changed. These all are considered as law of definite proportions. I'm just telling the name for your own ease, since this is the name, this is the law that you're going to find whenever you're going to consult the reference books or internet. You do not necessarily need to remember this name of this law, but you do need to understand and remember the points that you can't make water otherwise. It has to be hydrogen, it has to be oxygen, it has to be in the similar number or proportion of masses. I hope it makes sense to you, right?
Yes, sir.
Good, great. Now, if that message is clear and we are so sure about the proportions and about the formulae or about the formation of substances, we can always work with specific amounts to find out what is going to happen in a specific experiment. Take a look at this example, example 6.4. If 0.24 grams of magnesium react with 0.16 grams of oxygen, and they produce 0.40 grams of magnesium oxide. Now, how much magnesium oxide will be produced by burning 12 grams of magnesium? Now, they solved this question, but before I get to it, I'm going to prove one more point. Take a look at this. They say that magnesium reacts with oxygen and they produce magnesium oxide. Okay. Now try and understand the point. This is 0.24, this is 0.16, and this produced is equal to 0.40 grams. Add these up, you'll get the answer to be 0.40. And here we already have 0.40, which gives us a very good idea that mass stays constant in a chemical reaction, which means you cannot produce mass or you cannot destroy mass in a chemical reaction. This is also known as, now this is another law. This is known as law of conservation of math, right? You might have already studied the law in class 6 or 7. We explain this law in usually lower classes, lower secondary classes, and this law is usually taught in another way that we cannot create math, we cannot destroy math, we can only convert it from one state to another state. You may convert a solid into a liquid or liquid into a gas, but you cannot add mass to it. It would always remain the same after physical change or even after chemical reaction. So in a chemical reaction, the total masses of reactants is always equal to the total masses of products. And being a Muslim, I believe in it. We humans don't have the capability to create mass. We don't have the capability to destroy mass. We can simply convert one state of matter into another. Only Allah Ta'ala has the capability to create or destroy mass. This is what we believe in. So there you go. The law of conservation of mass is saying the same thing for humans. Okay, make sense?
Yes, sir.
Good, great. So if you understand this now, I think you can clearly understand why this question adds up in such a way. Okay. Now, if it adds up to in such a way, we can always calculate for 12 grams of magnesium, but I don't tend to do this question this way. It's a lot lengthy and it's a lot theoretical. Let's talk about this. So magnesium produces magnesium oxide. So we can pick any one of these. If magnesium used is 0.24 grams, which is this for magnesium, and it produces this for magnesium oxide, which is 0.40 grams. What if I use 12 grams of magnesium? What's the answer over here? That would be X. Now it is a simple ratio question of mathematics. Ratio and proportions are solved in the same way. I hope you understand we can easily put a dividing sign on both sides. And it's really easy since x is going to move over here, 0.24 is going to move over there, 12 grams is going to go over there. So it's going to be 0.40 grams multiplied by 12 grams over 0.24 grams. Grams and grams are going to cut, just this gram is going to stay. And how we know? Okay.
Yes, sir.
So if you can go ahead and remove the decimals, which we can easily remove since there are two decimal points up top and two at bottom, they're going to both multiply by 100 and we can simply remove them. So we can easily cut these parts out. We are left with 2440. So 12 to 20. So the answer to X is 20 grams. You see?
Yes, sir.
Which is also the answer over here, which the same answer is calculator is going to give you. Okay, makes sense?
Yes. Yes,
So
sir.
I'm trying to make more sense out of it. Here's how we do this. Now, what I did is that something the information has already been given about is put on your left, for which we need to find the information is put on your right. He simply asked how much magnesium oxide. So we know magnesium oxide is something we need to find information about. Put it on your right. The information is given for magnesium only. It's not given for oxygen, though it was given for oxygen in the start. But here the question is specifically asked with the help of magnesium. So put magnesium on your left, magnesium oxide on your right, and that's how your question should go.
Yes, sir.
Okay, you can't take oxygen and magnesium oxide since the whole information for oxygen is not present over here. The question specifically asks us the amount of magnesium oxide by giving us the information for magnesium itself, not magnesium oxide. Okay,
Mm, जी, sir.
I think this is good enough for today. So I'm gonna clear this whole thing up and we're gonna start with some more questions in the next working. All right.
Okay, sir.
Any questions?